In this video, we will do a table of probabilities example. So the example says, the table below describes a probability distribution of SCU students' plans immediately after graduation. So the table has a row that is labeled X, and these each describe a different event. So for example, there's employed and are working after graduation, or take at least 6 months off after graduation. And then underneath that, there's a row that's labeled P of X. And the way that we interpret those is those values are the probabilities of the event listed directly above it. So the probability that a student will be employed with work is 0.5, whereas the probability that a student will go to graduate school is 0.35. Okay, and then the question is, what is the probability that a randomly selected student, part A, goes to grad school? All right, so I want to know the probability that a student goes to grad school immediately after graduation. And looking at the table, the value for graduate school is 0.35. And that's the probability. If I wanted to write this as a percentage, I could. I multiply this by 100, which moves the decimal place over to the right 2 spots. So I get 35%. To convert a decimal to a percentage, I multiply by 100, and then I make it a percent. And that's our answer right there. So let's do another part to this example. So part B of this question asks, what's the probability that a randomly selected student does not take at least 6 months off? So I want to note a key fact about this. So if we go back to the table tells us the probability that a student does take at least 6 months off, and that's 0.1. But this question is asking about the probability that they do not take at least 6 months off. So that's the complement of this event. So I want to note now that the probability of taking at least 6 months off, that a student takes at least 6 months off after graduating, if I add that to the probability of the complement, which is that the student does not take 6 months off, those two probabilities should add up to 1. So in general, what we're saying is if you take the probability of some event, let me call it M, and you add it to the probability of the complement of M happening, well, those two events, M and M complement, collectively, they describe everything in the sample space. So when you add their probabilities, that should give us 1. I'm going to put that in a little bubble here. All right, and this question told us what the probability was, that they do take at least 6 months off. So this probability equals 0.1. So if I want the probability that a student doesn't take at least 6 months off, I just got to subtract that 0.1. So this will equal 1 minus 0.1, which is 0.9. Or if I wanted to write that as a percentage, I multiply by 100, and this would give me 90. 90 is a percentage. So that's our probability. So one final part to this example, which asks, what's the probability that a randomly selected student does some type of work after graduating? So let's look back to our table. So in the table, there's 2 types of work that are described. There's employed work, so that's like having a job, for which you earn some sort of salary for. And there's also service work. So for example, being a volunteer. So let's keep that in mind. So part C is essentially asking, what's the probability that a person does employed work or they do service work? It's got to be one of those 2 things if they're doing some type of work after graduating, according to this problem. And that's just going to be equal to the probability that they do employed work plus the probability that they do service work And if I add up those values from the table, probability of employed work was 0.5. The probability of service work was 0.05. So this adds up to 0.55, or as a percentage, that is 55% if you multiply by 100. So that's our probability. So the key thing that I want to make a note of here is that when we found the probability of something or something, this was the probability of a union of two events. Probability of A union B. So sometimes the probability of a union, as we saw here, is going to be equal to the probability of A plus the probability of B. And that's going to be the case if A and B are disjoint. If they're not disjoint, if there's stuff in common to both A and B, or two sets, we'll have to subtract away the probability of the intersection of A and B, similarly to what we do with sets. And we'll see an example of that in a later section. Okay, I'm going to put a bubble around this. That's what we use for part C here. So in terms of our goals for this section, we finished our third goal, which is talking about properties of probabilities and how to apply them. Over the next 2 videos in this section, we'll do some examples where we compute probabilities using both set and counting techniques.